Chapter 4 Higher Order Differential Equations. At the end of this video, you should be able to acquire the basic theories related to the solutions of higher order homogeneous linear differential equations. Linear differential equations, especially second order equations, are important in the study of differential equation because they are vital to the investigation of the classical areas of mathematical physics such as fluid mechanics, heat conduction, wave motion, or electromagnets. Another reason is that linear differential equations have a rich theoretical structure that underlies a number of systematic methods of solution. In this chapter, we will examine some of the underlying theory of linear differential equation and the methods of solution for certain types of linear differential equation. In order to present the key ideas in the simplest possible context, the methods of solution for second order will be described first, and then these methods will extend directly to linear differential equation of third order and higher. In general, an nth order initial value problem has the given form. Recall that an unknown function y of x, which is the general solution of a differential equation, is subject to the n initial conditions specified at x naught. Since the differential equation is linear, the dependent variable y and all its derivatives are of the first degree, that is, the power of each term involving y is 1. Each coefficient depends at most on the independent variable x. Assume that the leading coefficient is not equals to 0. G of x is called the input function or driving function. If g of x is equal to 0, the equation is called a homogeneous equation. But if g of x is not equal to 0, the equation is called a non-homogeneous equation. Example: determine whether each of the following differential equations is linear or non-linear, homogeneous or non-homogeneous. Solution: equation A is linear and homogeneous. Equation B is non-linear because the coefficient of the second derivative depends on y, and non-homogeneous because g of x is equals to cos x. Equation C is linear but non-homogeneous because g of x is equals to e to the power of x. Equation D is non-linear because the power of y is 3 and the equation is homogeneous. And lastly, equation E is linear and homogeneous. The generalization of existence and uniqueness of solutions for the nth order linear initial value problem is given by the theorem in this slide. Specifically, if the leading coefficient is equals to 0 for some x, then the solution of a linear initial value problem may not be unique or even exist. In other words, there is no unique solution of the problem. Example: it is easy to verify that the given function is a solution of the initial value problem y double prime minus 3y prime minus 4y equals to 0. The differential equation is linear with the leading coefficient is equals to 1 and all the coefficients as well as g of x are continuous on any interval containing x equals to 0. We conclude from the theorem the solution of the initial value problem is unique. Another example, the differential equation in this example is linear with all coefficients as well as g of x being continuous on any interval containing x equals to 0. However, the leading coefficient is equals to 0 when x is equals to 0. Hence, we conclude from the theorem that the solution of the initial value problem is not unique. In the next section, we will discuss the theories of homogeneous linear differential equation by the assumption as given in this slide. Theorem, superposition principle. Unlike the first order differential equation, the solution of the nth order homogeneous linear differential equation may contain more than one solution. Let y1, y2 until yn be n solutions of the homogeneous linear differential equation. If C1, C2 until Cn are arbitrary constants, then the linear combination is also a solution of the same differential equation. Look at the example. It can be verified that y1 of x equals to cos x and y2 of x equals to sin x are solutions of the second order homogeneous linear differential equation y double prime plus y equals to 0. Any linear combination of this solution, such as given in the slide, is also a solution of the same differential equation. The superposition principle implies that the sum or superposition of the two solutions y1 and y2 is also a solution of the given differential equation. Therefore, the general solution of y double prime plus y equals to 0 is given by the linear combination of y1 and y2. Linear dependence and linear independence. Two non-zero functions, f1 of x and f2 of x, are said to be linearly dependent if one function is a constant multiple of the other for all values of x. Otherwise, they are said to be linearly independent. From this definition, we can write the linear dependence of f1 and f2 as a constant multiple of each other, that is, either f1 equals to kf2 or f2 equals to kf1 for some constants k. We can see that the linear dependence of f1 and f2 implies that there exist two constants c1 and c2, not both zeros, such that c1 times f1 plus c2 times f2 is equals to 0. Conversely, if c1 and c2 are both zeros, then f1 and f2 are linearly independent. The analog of equation star is given by the next definition. A set of functions f1, f2 until fn is said to be linearly dependent if there exist constants c1, c2 until cn, not all zeros, such that the linear combination is equals to 0 for every x. Otherwise, if the constants c1, c2 until cn are all zeros, then the set of function is said to be linearly independent. We are interested in linearly independent solutions. We can verify if a set of n solutions is linearly independent using a determinant called a Wronskian. It can be observed that the Wronskian in this slide is either identically 0 or never 0 for every x. Theorem, criterion for linearly independent solutions. The theorem in this slide provides the case for linearly independent solutions by using the Wronskian. From the theorem, the solutions y1, y2 until yn is linearly independent if and only if the Wronskian is not equals to 0 for every x. Go through the example by yourself. Fundamental set of solutions. A set of n linearly independent solutions of nth order homogeneous linear differential equation is also called the fundamental set of solutions. The general solution for the homogeneous equation is given by the linear combination of the sets of fundamental solutions. Try this exercise.